All right. Thanks for coming along and braving the cold weather. It's nice and warm in here. Can I just start off? This is actually an auspicious day. Anybody know why?
It's the first time we're using a new AV.
No.
Nope.
Well, yes and no. Yes, but yeah.
First presentation with our flash news screen.
Yeah, well, that's another one, but there's another one that's slightly older than this. It's 128 years old.
It is the formation of Wild WIA in Tasmania.
No.
I'll
put you out of your misery.
When Lawson's message got here.
No.
Something to do with
Mr. Marconi patented, and the patent title was The Improvement of Transmitting Electrical Impulses and Signals, aka wireless. Back in 1897, so 128 years ago. Anyway, welcome to Dr. Stephen Newbery and Dr. Andrew Klekociuk. Now, I'll just outline a little bit about and introduce Stephen. Very long career, has recently retired from a career in space physics, health physics, and areas you're going to hear about. This is all about a project that Stephen was doing for your PhD?
Sort of, yeah.
Sort of, okay. And it is also looking at potentially resurrecting this piece of equipment, which may, after this talk, interest a few people in the room. So, now, Stephen's just recently retired, as Andrew as well. Seems to be a bit of a theme going on here. But also, can I just say, to get two atmospheric physicists in the room at the same time,
without annihilating each other.
Correct. Outside of a probably a climate change conference or something, is probably pretty rare. I have no doubt we'll learn a lot more about the chirp Ionosonde as we go into the talk. Can I also introduce, for those who don't know, Andrew Klekociuk, also from the Antarctic Australian Antarctic Division as an atmospheric physicist. As I said, recently retired, but also Andrew's continuing a whole lot of research in the background. Is also wanting to become an amateur radio operator. So I'm also looking at Stephen here. Don't do it. But involved in a huge amount of research. Some of the research is also working with Rex around auroral scatter and a whole lot of other areas. So, and can I just say, also has a very impressive all-sky camera, which is absolutely fascinating, and a whole lot of instruments associated with that as well. So, but anyway, so Andrew's come along and will be giving us a little bit of a presentation on the propagation, interpretation of propagation tools that are available. So, without further ado, I'll hand over to Stephen. Welcome.
Well, thank you for inviting me tonight to give a talk on something that was many years ago for me, and hopefully I'm resurrecting some of that interest in retirement. The talk, seeing the expertise and the knowledge of people around here, might be a little bit superficial, but I thought it was a good way to introduce who I am, what I've done, and maybe can fit in, and possibly impart some of the knowledge of the things that have gone out there that you hear about, and you don't fully have full awareness of where they've come from. So, Ionosondes and ionospheric radars and a vintage Barry Research Chirpsounder is the talk. So the first part, I'll talk a little bit about Ionosondes and what I did with those, and some of the novel techniques that people still apply and use today. And then I'll show you something that's circa 1970s, which I reckon everyone will love. It's packed full of 7.4 series ICs, and lovely tunable filters and big heavy chassis. So that's to pique people's interest, and never know, I might get someone that says, I want to give you a hand getting this going. So yeah, I graduated from La Trobe University with a PhD in space physics. I studied ionospheric absorption, HF absorption, which most people associate with the D region because that's the strongest absorbing region. But the purpose of the work was to look at collision frequencies. So with the more modern Ionosondes, we could do that, and you could look at the E region, the F1 and F2 regions, and look at the effective electron collision frequencies. So that was what I was doing. I had a brief stint as a research fellow at University of New South Wales, fabricating, designing and building infrared charge couple devices, which was interesting, working with microelectronic fabrication and testing. Then I went back to my other career, research fellow at University of Massachusetts Lowell, and there was a team of us there building a digital portable Ionosonde. And research money goes up and down in this world, and Lowell was always juggling US Air Force contracts, and so after I'd done the pulse compression circuitry for that, I got moved to be a contractor at Hanscom Air Force Base in Massachusetts, and we were working on survivable communication for the ballistic missile office. So when they say launch, they want to make sure the probability of their message getting through is 99.99%, and they have a myriad of ways of getting that message through, an absolute myriad, and Meteor Scatter was just one of those. Then I spent the last 30 years of my life working in the public service and doing none of that exciting stuff. I was a health physicist for the Department of Health in Tasmania, and I'm now retired, and I'm the owner of a Barry Research Chirpsounder. So I'll step through some of those briefly, just to give you a flavour, and then I'll talk about the Chirpsounder. So that's about circa 1980. This was my PhD. It's a vertical incidence sounder. The one over on the left is a Model C4 Ionosonde designed by the National Standards Bureau of Standards, US, NBS. It was a standalone Ionosonde, vertical incidence sounder, probably around 30 kilowatt pulse power. Came with all the jiggery-pokery and clutches and spinning frequency dials and whatnot, and camera assembly and so forth. It shipped back from the Antarctic on the deck of a ship and was a wreck when it arrived at La Trobe, so that was refurbished. There was a PhD student who added some add-ons, a receiver and digital counters, so you'd sense the ground pulse, start a counter, stop the counter when the echoes have arrived, and you've got your group delay in time and height when you multiply it appropriately. That evolved a bit into this. So here's a general radio frequency synthesizer, an 8-bit 8085 64K system that I built. And I was quite proud of the little screen that I'd spray painted. The receivers and digital counters, and the computer, and a 2400 foot tape for data recording. So basically it's a pulsed sounder. People like short pulses because it gives you good resolution. Takes up more of the spectrum, but there's that game you play between that. This was quite a long pulse sounder, 200 microsecond, which is a 60 kilometre pulse, but it had incredibly high resolution. I'll give you a little brief explanation of that. So really, the schematic would be familiar to everyone. 30 megahertz IF down to the final 50 kilohertz IF, and the phase counters are running at 18 megahertz, so it's 1 degree per cycle. You sense the first negative crossing as the ground pulse comes through. The transmitter's about 400 metres away from the receiver, separate antennas. You start the clock, you stop the clock, and you've got a number of degrees of phase between you and the echo. The reason is that the phase sounders, well, it's just a timing diagram, but it's neither here nor there. The damping, is it critically under or over damped? I can't remember. It was 2 exponentials, and basically ground pulse gating. The AGC had quite a dynamic range, and I upgraded that to be controlled by a microprocessor, so it would just sense the peak hold, put gain in there, and you would measure group and phase from those. So the PPI had a very long pulse, as I said, but it used a pulse synthesis technique, which, if you think of it, as you sweep over a frequency range, each frequency you've transmitted can be considered to be a component of another synthesized pulse. So if you measure the amplitude and phase of your sweep, you can then, using Fourier transforms, reconstruct the pulses. And the more points in your time series, the more resolution you can get. So that was the strength of the pulse ionosonde. And you can start to see, you could synthesize a pulse here from so many samples, and then you could resolve it into 2 echoes quite simply. So you could have this long pulse, but you could get short resolution out of them. The other thing you can do is, if you measure the derivative of phase with respect to frequency, you can get a precision group height. So this bottom curve is just measuring time of flight with the inaccuracies of trying to detect an edge and wiggles around a bit. This is from a phase measurement over 2 frequencies, so delta phi over delta f, and you can see we're starting to see structure of the order of 100 metres. So as travelling ionospheric disturbances, or a neutral gravity wave pushes the ionisation up and down magnetic field lines, you'll get rises and falls in the ionisation. So we could study things like that. Step forward a few years and it still looks ancient, because that's the way people package things. This is circa 1990, and this is the Digisonde portable sounder that I worked on. One's still in the Antarctic, and you can see the vintage by the floppy disk and a bit of a hard drive. Basically, it's a commercial PC, top of the line, in 1990, pulled apart, chassis embedded in that with all the RF, turnstile magnetic loop antennas. And this was a much bigger system. It was an interferometry array on the receiving side of things, so we could do angle of arrival. It was also a pulse compression sounder by using 2 8-bit complementary codes, GOLO codes. And the great thing about those is the people that know more about the spectrum than me, that when you do the correlation on 2 codes, you get a very strong peak. You get a lot of signal processing gain out of it. In fact, it was transmitting about 300 watts peak power, and after you did some coherent integration and then pulse compression, it was equivalent to probably transmitting 50 kilowatts. So you were getting a lot of signal processing gain. And it was a Doppler radar as well, so you could study ionospheric drift and ionisation changes. So I worked on that for a while, but as I said, money moves around, and then I got sent to, well, just to show how complex it was, it's 4 receivers, 4 of everything. The DSP card was custom built. It was based around a Texas Instrument arithmetic processing unit, custom software. At the time, they were hoping to get the Telstra, were hoping to get the OTH contract, and they were partners with Telstra, and they would do the frequency management support, but that all went in another direction, so that didn't happen. Hence, I went to the US Air Force Research Lab, and the survival communication there was to do with, our part of it was VHF Meteor Scatter. So we had a 45 megahertz system, transmitter, receiver, single conversion baseband. The transmitter just had 400 hertz tone on it, and very straightforward receiver. It just went convert, and if I've got 400 hertz here, the phase lock loop just sent out a flag saying yes, I've got a signal, and that plugged into a standard off-the-shelf PC with some custom software. The nice thing about it as survival communication was that what they were worried about was nuclear airbursts, and then losing the satellites, losing communication through airburst, losing landlines. Around the 40-50 megahertz, the ionosphere comes back quite quickly. So meteor is pretty survivable in that sort of thing. And the idea would be the meteor scatter would support a UHF point-to-point cell network. So they had these mobile missiles and they would be all over the US, and you'd just get your meteor message into one part of the cell, and then you propagate it point-to-point through UHF to the rest of the missile network. With adaptive modems that squeak the last bit out of the decaying trail. And that was the point of our project, to look at the trails and what bit error rates and what bit rates you could support, and probability of your message getting through and the accuracy of that message. The other great thing about meteor scatter is low probability of intercept. The transmitter and receiver sit at the foci of an ellipse, and any trail that's tangential to that ellipse supports a communication path, and no one else can really hear it. So that was that work. So I've done a few things in RF, but that was a very long time ago. And yes,
With regards to your 400 hertz and your meteor scatter, is there any Doppler phase or anything involved in that? Because it's locking on to 400 hertz, but could there be any variation in the 400 hertz and the transmission and then the reception?
not enough to,
Okay.
no.
All right.
Yeah, but as the meteor trail expands and diffuses, there's ionisation changes, which changes the refractive index, and that is measurable,
Yeah.
but it didn't affect that causeway of detecting.
Okay.
Yeah.
Okay.
So, with that brief background, I did a foolish thing at dinner one night, and I said to my ex-PhD supervisor, "You don't use the BR Research Chirpsounder anymore, can I have it?" And he went, "Oh, in principle, I can't see why not." They had bought a digital sounder like the one I showed you, the Digisonde portable sounder. And one day a car turned up in my driveway with all this equipment in the back, and I was the owner of the BR Research Chirpsounder, which I had visions of firing up and doing oblique studies, very much like the Tiger radar on Bruny Island does. At the time it was a Latrobe, it couldn't quite had the legs to make it to the Auroral Oval and back, unless you beefed up a lot of the transmitter and the TR switch. So I thought, now I'm in Hobart, I'll do it. And that was pre-Tiger, but that didn't happen. And life has a way of doing lots of things to people, so it sat in my shed for a long time. So yeah, the Barry Research Chirpsounder, Fenwick and Barry in the 60s came up with the technique of using chirps, which is fairly common. People use chirps for a lot of things, even I think modern day gigahertz chirps for autonomous vehicle navigation is used. They came up with a way of using it for sounders, initially oblique sounders, but they fiddled around with it a bit to turn it into a vertical sounder. It's a type of pulse compression radar, the chirp, and you coherently sort of squeeze it back on itself through the time delays. This one uses 25 kilohertz linear frequency sweep segments. And as I was saying to Andrew in the car, in principle, the simple hand waving explanation of it is quite straightforward. To make it work in vertical incidence, it's a little bit more complex engineering to have a sequence of chirps. But the bottom line is it probably, it's equivalent to a sort of 45 microsecond pulse when you think of that chirp. The way it's compressed, it's about a 45 microsecond pulse, which is typical for most pulsed ionosondes, are around 50 microsecond pulse to give that sort of resolution. And you can see it looks very much 1960s, 1970s technology.
Stephen,
Yeah.
what frequency we talking?
0.5 to 30 meg. So
HF?
HF. So most of the usable ionograms are in the 2 to 20 megahertz, depending on the solar cycle, 20 meg. But D-region absorption F-mins usually hovering around 2 meg. Yeah, so it's an HF Ionosonde.
That
Yeah.
makes it an MF, doesn't it? 2 meg.
Yeah, well, 1600, I guess. The end of the broadcast bands were about 16.
3 meg, isn't it? 3 meg to 30 meg. HF.
HF. Yeah,
Sorry, Richard.
that's all right. Yeah, so this is a simple explanation of how the linear ramp controls the frequency for the frequency modulation. The more I've read the manuals lately, the more I've pulled my hair out, because the clever people that engineered this have got some really interesting circuitry in there to make it do what it has to do. So in principle, the block diagram is really simple. You've got a linear frequency modulated transmitter, goes up to the ionosphere, it comes back, and you mix that with the copy of running the same linear ramp. The guts of the thing is the spectrum analyzer, because the frequency between the two, well, I'll get to that in a sec, is what gives you your time, your delay, your range. And this was a modern diagram. It has a PC. Mine has camera, film, and an oscilloscope. So the overview of it is, and give you a sense of scale, that's about as tall as me. And wow. Each chassis is about this big and heavy. So, like any radio system, we've got a bank of local oscillators, a receiver, a log chirp controller, and that is a monster. It's 30 PC boards about this big, stacked full of 7/4 series counters, gates. It is the important part of controlling the chirp. But pretty standard amplifier and transmit receive switch. Having said that, the transmit receive is also complex, because you can't just launch a chirp and then say it'll come back to me and I'll do a spectrum analyzer with it. You're going to get reflections coming back low down and high up. So it goes through a sequence of small transmit, listen for a while, small transmit, I'll ramp a bit, I'm a chirp, I'll do this. It's a very complex series of transmitting, receiving and chirping, which I still haven't quite drawn out properly yet, and they haven't drawn it out for me. And the critical element is a frequency synthesizer. It's just a standard sort of design for its day, and it's got a BCD input, so you dial up the frequency you want from your log chirp controller or from nowadays a PC. An audio spectrum analyzer, which is beautifully built, but could now be just software in a card this big, I guess. And the 35mm camera system. So the output, the video output from the spectrum analyzer is pretty much just amplitude time, and it would go into any oscilloscope. It just happens to be they put a Tektronix one and customised it into theirs. And this was the photographic system, which I don't have. It was a 35mm system to produce archivable records of Ionograms.
What sort of power supply do you need for it?
Not much. It's probably like running a couple of PCs, because the RF side of it is a lot here.
300 watts?
3 watts average.
Yeah,
8 watts peak, yeah. So signals are generated by the synthesizer, by the log chirp controller. The output from the synthesizer is approximately 3 watts average. 8 watts peak. So it was loved in Europe because it's spectrum friendly. You haven't got these Ionosondes with big pulses and short pulses, clobbering people and having, it also has some interesting features inside it for blanking frequencies it found that were interfering with it. I don't know how they did that. I haven't drilled down to that. So the transmitted signal, like any radar, goes up to the ionosphere where it's reflected. The reflected signal is delayed in time due to the distance travelled. That's pretty standard. It's then received and mixed with a copy of the transmitted signal through the receiver IF chain. And the output comes between 0 and 333 Hertz for the spectrum analyzer. So just to put that in context of the ionosphere, I've got a very generic ionogram here with the E layer, F1 and F2 layer, and I pluck some numbers out of the air. So it's say 100 kilometres for the E layer, somewhere around 2 to 400 F1, F2, and the system has a maximum range of 1,000 kilometres in it built into its design. So if you just do the time of flight for those, you'll get that many seconds for each one. And you've got a 25 kilohertz, 50 kilohertz per second FM chirp. So the frequency differences will be 33, 67, 133 and 333 hertz. So basically you see a 330 hertz peak coming out of your spectrum analyzer. You know that it's a 6.67 millisecond time delay, which relates to 1,000 kilometres. So they're completely translatable between frequency, and that's just a expression of that. You've got a transmitted signal and a received signal. You time shift it, and then when it's mixed with itself, it's going to be a few hertz difference, and that's what the spectrum analyzer will sense out of the IF chain from the receiver. Right. For the Chirpsounder in 2025, it sits in my garage. Again, there's the components, not in the same order as the photo, in a sort of jury-rigged 19-inch track.
Bits of wood.
I had to put the beautiful trays that sit in there went missing. Yeah. The Antarctic Division kindly stored. My wife got sick of it occupying the front bedroom of a house, my cherished possession, and she said the children have to have a bedroom. So Gary Burns said, "Oh, I'll put it down the Antarctic store." I said, "Thank you." And I went down there, and then they were having a clean out, and they said, "We can't do it anymore," so I had to bring it home again. And the rack, the little shelves were gone. But anyway, I worked around it. I screwed some bits of wood across. So we have all the components except for the film system and an oscilloscope. So the oscilloscope's neither here nor there. And now that I've retired, and there's a whole group of people that know heaps more about electronics than I do, they might get excited by this and decide that amateur radio could do with an Ionosonde. So plan A is proof of life. Let's put the power on and see what happens. After having blown all the dust and cobwebs out of it and checked for some basic things. I think the critical items are the frequency synthesizer and the spectrum analyzer. Constructing those is a bit of work. The spectrum analyzer with the 0 to 333 hertz and some TTL syncs, it does it all for you. It says you're going to get an echo now and look for it, and it gives you a 5 volt TTL output for that on a BNC. Sync, spectrum output, beautifully set up to plug straight into a computer. That's my hope. So that's the spectrum analyzer. If the spectrum analyzer doesn't work, then plan B would be, well, receivers, amplifier and local oscillators, while it might be a pain to make them work, they're things you can fix. I understand RLC and power supplies and stuff, and with a bit of elbow grease and an oscilloscope, you can toil away at it, you could do that. The synthesizer, I'm a bit more dubious about. Its replacement would be expensive. However, the current spectrum analyzer and log chirp controllers are complex, and they make use of a lot of 7.4 series ICs, and it could be high maintenance and they might not work. I should say this thing was working when they gave it to me, and it's been stored fairly well, so who knows. But in principle, the spectrum analyzer and the controller are amenable to software. Anything that's a big box of counters and flip-flops and timers is a piece of software, basically. And the spectrum analyzer is an audio spectrum analyzer, so the PC is very capable of doing that.
Do you have the circuit diagrams?
Yeah, I kicked myself. I knew people would love to see the old. It's very well documented. It's got every schematic, circuit diagrams, parts lists. You could build one from scratch if you had to. That's how well it's documented. I meant to bring it in just to whet the appetite.
The knobs look familiar.
The switches look like what was on a mini scamp.
So that's the log chirp controller with the Nixie displays and beautiful knobs. I should have cleaned up for the photo, but I thought I'd just
American cobwebs or Australian?
Australia.
Vintage cobwebs.
Kingston cobwebs.
You don't need to import cobwebs, are we?
So if it works, there's two possibilities, all revolve around this. One would be if we've got a functioning spectrum analyzer and enough of the system goes to produce the output we need, then with that amplitude frequency, the spectrum, and the appropriate sync pulses, we can recreate an ionogram digitally. Quite simple. Just frequency tells you the time of delay, and you know the frequency because where you are in the chirp. So that's pretty simple. The next fallback would be that's not working, but the receivers are still working. The receiver's given an output to the spectrum analyzer. You could actually perform the spectral analysis in here and then recreate the ionogram. Yeah, so that's the Barry Research Chirpsounder and a bit of the things I've done. I'm still scratching my way through those bloody manuals because it wasn't part of my PhD. It was the instrument to operate a site, to be part of a worldwide network and have archivable records you can swap with other people today. So I might push a button on it occasionally, but I never used it. I used the other gear that I built. So yeah, happy to answer any questions if I'm capable.
What was the antenna system that would have been on the Barry Research?
What was it?
What was it?
An inverted V. Broadband, that's what I can remember, inverted V.
So two of them?
One, no.
One. So
Yeah,
TR.
that's-
Yeah. Okay.
Yeah, if you had two, you'd still be receiving what you're transmitting.
No, well and truly.
And you'd, whereas on the pulse systems, I was happy to receive what I was transmitting. The ground wave didn't bother me because the AGC would clamp it right down, and I needed to trigger on that with my phase counters, and then I could wind the gain back up for an echo, and then wait for the echo to come through and mesh the phase again. This thing, as a bistatic radar, you'd need to operate it obliquely over big distances, which is what they have been used for. Or in the early days of Dawn, Jindalee over the horizon, they use ground backscatter. So FMCW ground backscatter. But this one was a single transmit-receive antenna, and hence this complex. I still can't quite figure it out. You've got a 180 microsecond transmit window followed by 4 of those windows to receive, and then you reverse it. And then they put a warble on that timing because some of the heights, you would have missed some of the heights if you stuck to that. Yeah, it's like a little bit of a workaround.
And they did all of that in Logic.
Yeah. There's synchronous counters and they get reset. And
What's the clock speed of the...
It's not that high. It's only in the single megahertz ranges. Yeah. And it can, it's better megahertz because you can drive it with an external one.
Up and control, that would be important, wouldn't it? The timing stability of that clock signal.
Well, the frequency synthesizer does give a stable output to drive things with, and it's in the parts per million. Yeah. So you can get a reference out of your signal generator and use it as a master clock for the system, and then it's just got a series of dividers in the log chip.
The 400 hertz tone on the meteor scatter for the nuclear deployment code. How was that modulated, or was it there's 400
There's
hertz, so we
400
launch?
Oh no! Yeah, that would be no. We weren't like. It was a research instrument to characterise communications channels. It wasn't for communicating.
Oh, okay, right.
So, meteor scatter is a bit of a parametric science. You know, you could model it and say, and they're just grains of sand basically. You can't. They're tiny, and there's a flux of them coming. I can remember we put up. They were 45 megahertz Yagis for transmit and receive, and we put it on top of a telegraph pole in New Mexico, and the other one was up near the Mount Rushmore area, Northern America. Just crept it around a bit, and we had an ICOM receiver.
South Dakota.
Yeah, ICOM receiver, and suddenly I heard beep, 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 400 hertz. Beep, beep. I said, "Is that how many meteors there are?" They're just streaming in all the time, and of different strengths and different trail strengths. So, characterising a channel, so you get that follows Poisson statistics. So, like the old statistics of phone calls arriving in an exchange, they're just random, but they follow that Poisson statistics. So once you've got enough data, you can start to say, what's my waiting time? What's my bit error rate if I've got my received signal lengths? Andrew's nodding his head because that's been your career, Andrew. So you need a database over that channel, and then you can start to say, well, if you use this channel, then you can get they'll pose the question, we want to get a 300-bit message through with 99% probability and a waiting time of less than this, and your database can answer that question then once you've got the data. Other people that were interested in it were Defence Advanced Research, DARPA. They wanted to reduce early warning radar data from Alaska, planned position indicator type data, which is pretty much just azimuth and target really. So it's not a huge amount of data. They wanted to back all that back to continental US on a series of meteor scatter as a survivable system. And they also wanted a portable system for drug interdiction. So they would lower people into Central America, would spy on airfields, and they see them packing planes full of cocaine. And because meteor scatter, it's very mountainous down there, you could shoot great angles of elevation, and the operatives could get a message back, and they could catch the aeroplane. So meteor scatter had a lot of uses. Ballistic missile officer was just one of their tools.
So there's enough meteors at all times.
Absolutely.
Okay.
It's just I'd call it a rain of it. Like, I was new to that field, and I just remember plugging the ICOM in straight to the bottom of the antenna, and I was just listening to them going beep, 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 long ones, short ones, just,
What distance were you?
I think it's a maximum range just from curvature and about 1,200 kilometres. I think we were from Mount Rushmore down to New Mexico was around the 900k mark.
Yeah, that's about optimum.
Yeah. Right. Well, thank you.
Will you need a license, an amateur license, to operate your Barry?
I need more than an amateur license. I was going to try and twist the thread of university's arm to. They've got a license for it, just the state's in a different spot.
Yeah, right. Okay. Only 3 watts. Who's going to know?
The phase path Ionosonde, one of the students, we had a transmitter, it was a 1 kilowatt portable transmitter, bell transmitter, and he decided to do some work on it, and he replaced lots of resistors and things, but he didn't realise how wire that. And so, and he took the choke filter off. So, with this frequency synthesizer, he can jump around frequencies wherever he wants. He blacked out northern Tasmania fire, Mildura air traffic control, and the regulators, they were doing all there, and just as they tried to triangulate,
He'd turn it off.
he'd change frequency. And they started over a period of a week to think it was malicious. And then they finally got a fix, and they drew these lines, and they go, Beveridge, Hume Highway, Victoria. What's that? Latrobe University Ionospheric Research Station.
Excellent. Thanks, Stephen, and thanks very much for the invitation to come along. I'm just going to add a few details to Stephen's talk, just probably to remind you a bit about some of the data that's out there through Bureau of Meteorology Space Weather Services. I'm sure you're quite familiar with a lot of this, but I'm kind of trying to work towards the end there to whet your appetite a bit about maybe some of the things we could actually do with Stephen's Ionosonde. And there's still quite a lot of gaps, I guess, that amateurs have got a role in filling. And I hope some folks here might be interested in listening to the chirps once we get things going, and I'm sure there are some good science outputs in there. So you're probably quite familiar with the HOMS Space Weather Services page, and I've brought up here the HF systems page, and there's a lot of stuff on there. I guess we're very lucky to have all this free information, and we can thank John for a lot of that, I think, because the Bureau obviously has John gingerly over the horizon radar as a client, as well as all the aircraft operators in Australia, and it even goes right down to radio amateurs. I think they're recognised as a key user. I look at this page quite a lot, but I guess the thing that you might not be familiar with is perhaps the whole network of instruments that are around the country which supports this. And Ionosondes, the dark blue ones there, are pretty important in giving us information on the state of the ionosphere, which is important for your MF and HF and even your VHF communications. I'm going to stick kind of in the HF domain, perhaps down a little bit into the MF, and I won't say anything much about the VHF, but we'll stick with the range that the Ionosondes are important for. But there are a lot of other instruments there. These days, GPS measurements quite important in surveying, and a whole range of other things. So there are instruments there that look at the electron content of the ionosphere or the ionised parts of the atmosphere, and particularly for ionospheric scintillations that can upset positioning. Some of those instruments actually have dropped off the list, and some come and go, and we still have instruments operating in the Antarctic, which is quite important for looking at the range of ionospheric conditions between Antarctica and Australia and beyond. Just to remind you, Stephen showed a little diagram of the ionospheric layers, and maintained by solar ultraviolet radiation, extreme ultraviolet radiation in particular, and depending on time of day, the key ionospheric layers during the daytime, we've got the F1 and F2 layers, which support the longer distance communication, the E layer and sporadic E at various times, shorter distance, and of course the interfering D layer, a lot of absorption there. And at night, the F layers kind of disappear or condense into a single layer, and the D layer disappears altogether. And it's interesting at the moment, I looked at the Ionogram from Hobart this afternoon, quite a lot of sporadic E, and I was looking at comms in Eastern Australia, and people seem to be making a bit of use of it at the moment. So interesting during the winter time to see that. And that's kind of an interesting topic for Ionosondes in general, the mysterious sporadic E, and trying to understand that a bit more, so just whetting your appetite for later on. Of course, the frequency that penetrates or is reflected back from the ionosphere depends on the ionisation state, the angle of incidence, and the key factor here is this critical frequency for vertical incidence, which dictates to some extent the range that you might get with oblique incidence communication. And I'm a radio astronomer, so I'm kind of interested in what's coming back the other way, as I'll show you in a second. But the vertical incidence critical frequency is one of these key parameters that the Ionosondes give us. And there are some simple relations for that, but it gets more complicated when you have extra layers of ionisation in there. Just to remind you of how this frequency varies with a few parameters there. I'm showing on the left a cross-section from the equator to the pole in day and night, and there are some interesting features there. In the daytime, we have this equatorial anomaly in the critical frequency, high critical frequency, which is related to this trans-equatorial propagation that some folks here probably make use of. At night, there is this mid-latitude trough, kind of south of Tasmania. So both of these anomalies, or the trough, are produced by plasma transport. and the mid-latitude trough in our region is actually a decrease in the critical frequency, which allows us to see the radiation from interstellar space. Actually, at our latitude, the ionosphere is transparent to fairly low frequency radiation. So University of Tasmania has made some very good use of that over the years in actually studying the cosmic radio emission.
Grove River.
Great Reaver, yeah, Bill Ellis, key people I was lucky enough to work with many years ago. Solar cycle is quite important in dictating the critical frequency of the different ionospheric layers, and of course we're at kind of a solar max, which is a little bit similar to around the year 2000 at the moment. It's sort of an intermediate solar cycle. It's not as weak as the more recent one. So that dictates your maximum usable frequency. And of course, there's a diurnal variation in the frequencies that you can use as well. So kind of, as you know, you get different propagation conditions depending on day and night. And you get some interesting effects around the dawn-dusk period as well, which is related to some of these ducting of propagation by the different layers of the ionosphere. So on the left there, a simple diagram just showing you that the various regions can give you different distances. You can get obviously scatter off the ground that Stephen mentioned from the E region and actually achieve long distances, but of course you have the issue of attenuation by the ground. And then there are complex modes where you can get ducting or reflection off the different layers, and this transequatorial propagation in particular is one which gets ducted by the ionisation anomalies in the F region in particular. And of course the ionosphere is not just a simple spherical shell. It can have quite complex structure, as Stephen mentioned, the atmospheric gravity waves, so the flow of air over mountains, particularly from Tasmania, propagating up and tilting the ionospheric layers and giving you a range of propagation conditions. Now, of course, on the Bureau site, they give you a lot of information based on observations by the Ionosonde network in particular. So this is a map just for the other day, kind of around early morning our time, and showing you the FOF2, so that vertical incidence critical frequency for the F layer, and being much higher in the daytime hemisphere and quite low at night. In fact, in the region of Tasmania there you can see values below 8 megahertz and in some cases down to even 4 megahertz. So that means that your F region is not going to support long distance by those frequencies. And you can look at this. This is based on real observations, which is quite nice. And actually, just a note there that so on this page you can actually look at this sort of tells you the maximum frequency that you could achieve between a base station, say in Adelaide, and anywhere else in the globe there. And you can see that little note there saying we're reviewing what charts should be produced for this website, and there aren't many for Eastern Australia in there. It'd be interesting to, if you're a radio amateur, you might want to see perhaps some other sites in there. I guess a site in Adelaide is probably quite representative of most of Eastern Australia, but there might be some others there. And of course, you've probably seen various ways of looking at what frequency coverage you might get across the globe. When I was a student way back, even in high school, I used to subscribe to these GRAFEX predictions that the former IPS radio and space services would actually freely send out to you. I used to get these once a week in the mail, and this one's actually for my favourite transmitter, which is WWVH in Hawaii. I used to monitor the signals for that, looking for shortwave fade-outs and other effects. But this gives you a graphical representation across the the UT day running down vertically, and in frequency running horizontally of what propagation conditions you might see. And I guess folks are familiar with this Voice of America propagation predictor, which is seems quite accurate. I use this also for looking at various sites, and this is another representation of the frequency coverage that you might expect between 2 points over a day. Now, as I mentioned, I'm interested in radio noise from outside the Earth, or even perhaps within its magnetosphere. So I'm quite interested in getting clear windows, and so I'm more interested in when the vertical incidence critical frequency is, well, as low as possible, but I have to contend with the variety of interfering stations, and Ionosondes are actually an interferer for me. And of course you can see Ionosondes or radars of various sorts. They could be over the horizon radars producing these chirps or sweeping signals. And the other thing you have to contend with is all of the background noise and other effects. Some of that is natural, so from lightning, but more commonly now we have all of these strange signals which come from things like plastic welding systems and laminators and all sorts of other things, and can come quite long distances. And in fact, in this case here, well, these little hooks and swishes, as they're called, are probably coming from Eastern Asia, according to this map of, this is FT8, I think, propagation as compiled by G7IZU. Quite a useful little site to see what's happening way down here in Tasmania, of course. So I'm interested in getting clear windows to look at cosmic noise. So just on to some of the key points of ionospheric sounding. Stephen's already mentioned the general purpose of an ionosonde, and that's to tell us something about the heights of the different layers, their virtual heights, because the speed of light in the medium is close to the speed of light in the vacuum, but not precisely the same. And when a radio wave is transmitted into the ionosphere, it splits into two components, the ordinary and extraordinary modes, and you get two echoes. In fact, there's a third mode, the Z mode, I'll mention a little bit later on, which is a rarer mode. So a typical ionogram will tell you something about the location of the F layer and the presence of any E layer in particular. There's often too much absorption to see a defined D layer, but there are a bunch of parameters that ionosondes use to scale, and I've mentioned this one here. This is the vertical incidence critical frequency, maximum critical frequency, the FOF2 value. And when you look at ionograms, which you can do on the space weather site, I'm showing here some daytime ionograms on the left for Canberra and the same time for Hobart. You can see some quite different behaviour between the two sites, and that relates to the magnetic latitude of the two stations. Canberra actually has a more modern ionosonde these days. It's a Space Weather Services 6A ionosonde. I'm not quite sure what the special features of that are, but it's producing some very nice ionograms. And down here at the lee, we have a
Andrew,
5F.
Out of interest, the guys that developed and constructed that was VK1XX, English.
Yes,
one
right.
of our hams.
Yes, fantastic. Yes.
Yeah.
And so that's, it'll be interesting. I see now that there's one of these at Casey, the 6A.
Yeah, not yet at Hobart.
Not yet at Hobart, but
Yeah.
looking forward to that, because it'd be nice to have a good quality ionogram to compare.
At the lee, did you say?
Yes, down just off the southern outlet. Been there since 1948, roughly.
before the Scouts, or
Before the Scouts, I think. Yeah. And back in the day, of course, it came back to that film recording systems that we use 16mm film. Yeah, but now all digital. And this thing's going off every 5 minutes, I think, or is it 15? Giving you some sounding. I guess the 6A actually seems to have a better tolerance to interfering noise. You see a bit of interference here, but on this particular occasion, this is just a few days ago, so this is 25th of June, early in the morning, 23:05 UT. You can see the F1 layer, F2 layer. This is a reflection off the ground going back up again. There's a third reflection there, multi-hop propagation. Quite well defined ionospheric layers, a little E layer in there. And then at night, quite different. And in Hobart, the ionosphere can be more disturbed. You can have auroral effects that give you a lot of spread. So there's tilted layers and gives you this kind of spread. And it can be actually quite difficult to determine some of these ionospheric parameters. But you can see quite a nice inlay in there. Sporadic elements.
So are those images tidied up at all? So the noise on the right hand side of the Hobart one versus the Canberra one, is that Canberra one been cleaned up in any way, or is that literally what we're seeing?
Yeah, I think it's doing some smart things these days. Rex might have some comments there in digital signal processing to suppress the.
Couldn't say
No.
it more than it. Glenn does whatever Glenn feels like doing.
how do you tell the difference from E layer and sporadic E layer?
Yeah. Well, generally these things are fairly ephemeral, can last tens of minutes, but generally they're classed as sporadic E when they have a fairly wide frequency range. That's my understanding. The general E layer, the density of it is fairly low, and it produces echoes only up to what's called the FOE frequency, which can be much lower. But the sporadic E can be quite dense and produce these echoes up to higher frequencies. That's my understanding.
Even up to 2 metres.
Yes, that's right. Yes, exactly. Yes.
And you can sort of work interstate on 2 metres.
Sporadic E, right?
Mm.
But that chart didn't go to 2 metres, did it?
No.
No. The Ionosondes generally limited to 30. I think the one Hobart's 22.
But you actually can, there's a multiplier for low angles, isn't there?
Yes, that's exactly right. Yes, that's that.
That's
Equation.
vertical instance.
Yes, that equation going back there with the sine of the angle.
Yep.
You can apply that to the E layer. So if you know the FOE value, which is, or if you knew, say, this upper limit frequency here, you could calculate for a particular angle of incidence divided by the sine of the angle, and that will tell you the maximum usable frequency for E layer propagation.
Yeah, okay. But like that layer there's petered out at 10 megs or 12
Yes.
megs or something.
Yes.
You wouldn't expect that to be working.
No, but if,
So-
if that got up to 25 megs,
Then-
that might run at
Yeah.
2 metres.
Yes.
Yes.
And even at 16 megs, it'll probably run at 6 metres.
Well, yeah. Because I guess when you've got low, with low angles of incidence, you get to higher frequency, but you're still limited by the height of the layer, the maximum distance that you can, the curvature of the Earth.
You need a good takeoff to take advantage of the long distance.
The amount of times it gets up to 2 metres though is proportionally less than 6 metres. A lot less. Like 10 times less or something
Yeah.
like that.
And you can do
Well,
two
it's
hops
pretty
as well.
exciting when it happens.
It is. Yeah.
You could do 2 or more hops too, of course. If you're transmitting enough power, and the layer is extending over a large enough area.
Is that also the case with the previous map that you showed of the BOM website where you've got the map of all of the colours and stuff like that? it'll be up to, like, as Rex said, sometimes 22, 25 megahertz, maybe out in the Pacific, and you'll get a couple of patches in there, and then you can look like you might get 50 megs over the Pacific to America.
Yeah, that's really only using the F2 value, not the FOE, and unfortunately they don't give you a FOE or FOES for sporadic map, which is something that actually could be evaluated, because as I'll show you, so in fact in this next slide here, so this is kind of showing you what the FOF2 value in real time is from the BOM network. And if you've come across this IRTAM website, it gives you a similar plot, but perhaps not as useful. I like the colour scale in the BOM plot. You can see these are actually at the same time, and I've got the same longitude range, and these are the Ionosonde sites that are going in there. It's Hobart. You can see here that this is the this is the daytime hemisphere. Values 9, 10 megahertz, but this is only in FOF2, not in FOE or FOES, which would be interesting to show. And you could actually generate this sort of thing too, if you're interested potentially. But yeah, this site's quite interesting. You can have a look at a bunch of Ionosondes from around the world on this. So one thing I'm quite interested in is, and it turns out that there's a bit of a gap, strangely enough, in this aspect. And I started noticing, so I monitor about 8 megs of frequency continuously with an SDR, and I have a few of these sort of dynamic spectral measurements. But there are some solar bursts here one morning that you can see come down to a certain frequency limit, and this is not the fact that the solar radio bursts from the sun are actually limited in frequency. This is the ionosphere doing this. That's my little observatory there. So theory says basically, as I showed you previously, it should be related to FOF2 divided by the sine of the solar elevation angle. But that doesn't work at really low angles. It works above about 20 or 30 degrees. But low down, there's actually ducting by the E layer potentially. And on this particular day, there's a little bit of E or D layer. A bit hard to tell really here. There's certainly a bit of an E layer in there. And so what's happening is that the solar bursts in the daytime hemisphere out to our east are actually getting to lower frequencies because they're being ducted, first bouncing off the E layer, then back up to the F layer, and then down again. And I'm receiving them. This little plot here is showing you that's the angle of the sun at particular times. And I've plotted here, it's a little bit complicated. I've plotted this critical frequency, which is this term here. But I'm showing you on the right-hand axis in the orange colour, if this worked, the orange dots should fall along this one line here, but there's actually a factor of up to 4 that you have to multiply this equation by to get the observation. So I'm trying to work through, I'm using this ray tracing system FarLab, which DSTO make freely available. You can run it on MATLAB, the free version of MATLAB, and you can put in all the ionospheric parameters, and you can use the local ionosonde to tell you, the FOF2 value and the FOE value here. And I'm working my way through trying to understand that. And there are a few papers out there that talk about this working above about 20 or 30 degrees solar elevation angle, but they don't tell you what happens at low angles. So kind of an interesting little thing. So ionosonde would be useful if you can get continuous measurements at a different site. You could be looking at the E layer in a little bit more detail. The other interesting thing I find is looking at the effect of solar X-ray and extreme ultraviolet events on the ionosphere, and here are some examples of shortwave fade-outs, which you guys probably find quite problematic. You know, you'll get a lot of absorption occurring after a large solar X-ray flare, which here's a schematic plot showing you a drop in signal strength at different frequencies, and it becomes more substantial at the lower frequencies. On my spectral system, you can see a decrease in these transmitters. I've got some local interference and some other spurious things in there, but a drop in some of these signals drop out, but also a drop in the background noise, and that's the other interesting thing. It drops out the whole range of interference that might be happening, which is propagating via the ionosphere, whether it be power systems or lightning and various other things. And Stephen mentioned travelling ionospheric disturbances. You can see those on Ionograms. Here's one I found last year where these quite strange looking echoes coming back from the F layer are because there are various tilts happening. And this is around the time I'm receiving here WWVH signal. I make Doppler measurements of that, and these little wibbles happening in the frequency, which are caused by movement in the ionosphere causing Doppler shifting of the layers, which is due to these travelling ionospheric disturbances. Happening actually before a large solar flare that dropped out the signal. These things can be related to solar flares, but they can be related to meteorological conditions.
Andrew, does that correlate with total electron content?
Yes, that's right. So you can be measuring total electron content with a GPS system, and you'll see an increase as these layers, you're kind of looking at a GPS satellite. If you're looking through a tilted layer, you'll see variations in quite complex. You'll get scintillations and all sorts of other things. But yeah, some of the bomb instruments are looking for those sorts of things. And a thing that you can do is you can go and download all of the scaled data from different Ionosonde sites. And what I've done here with this FastChar site is I've grabbed the what's called the FOES critical frequency for Hobart over the last summer. And of course, if you're interested in when these sporadic E events are occurring, this is a good indication. Here's an example up here where it's up around about 18 megahertz, and here's the E layer on that particular day there, and we're getting multiple reflections and some ionospheric disturbances going through. So one thing that is quite interesting is the occurrence of sporadic E and what's controlling it. And in Hobart, it's interesting. I think there are some large-scale atmospheric processes coming from the Antarctic that can potentially influence sporadic E, and that's relating to creating wind shears in the ionosphere, so waves propagating up through the atmosphere. So our little project is to try and look more regionally in southern Australia at these events, and Chirpsounder would be quite useful in that. Now, just in the closing couple of slides here, so just reminding you, if you haven't come across HamSci, they're developing this personal space weather station, and some folks are getting into doing oblique ionospheric sounding by looking at chirpsounders and other ionosondes. And this is all mainly done in software. They have one of these SDRs that's actually got quite a wide bandwidth, 60 megahertz bandwidth, and some Python code that basically you're recording the IQ signal out of this SDR and then post-processing to find the chirps and to look at the characteristics of the ionosphere obliquely using that signal. Now, oblique ionograms can be quite complex to interpret because you're getting scattering off potentially multiple reflections from the ground and the ionosphere, and also tilted layers have quite an effect. But with a network of these, as kind of Steve alluded to, oblique sounding systems, you can build up a regional picture of the ionosphere, which you can't really do just from a single site. So have a look at that site. Some folks might even be able to get into that using the local Ionosonde or other Ionosondes. And I've had a bit of a go at it. You know, I think I've generated a couple of things that look a bit like this, but I really haven't got into understanding what I'm seeing yet. Another interesting thing is this other branch of propagation in the atmosphere, what's called the Z propagation hole. And Bill Ellis, who was professor of physics at uni, was one of the first to actually understand this. And I mentioned that a wave will split into two components, the O and the X mode. The X mode can split again when you have a strong enough magnetic field and create this Z mode, as it's called, which propagates into the F region. And the property of it is actually you can get signals coming back through the Z mode, so from the galaxy, or from auroral radio noise, which might be produced in the lower thermosphere, or you can use it actually to heat the atmosphere and do some interesting sort of physics studies, as they do at the HARP facility in Alaska. But this Z mode is quite rare, and still understanding how it occurs, it's basically related to some thin ducts that appear in the F region. But having a chirp sounder, particularly operating down at these low frequencies in Hobart, another one alongside the Bureau's one at a slightly different site, would actually be quite useful for understanding the Z mode, particularly if you could beam off in a slightly different direction, not necessarily vertically. So that's quite an interesting thing. Still a lot of work. If you look through how many papers have been published on this, quite rarely studied, but potentially of interest to folks like me that want to look at the galactic radio emission, or find out when you can observe down to these low frequencies. And then another thing which I have some interest in, but I think it's actually probably a stretch to actually study even with a chirp sounder, are these long delayed echoes, which people might not be familiar with. So just like Whistler waves at VLF, you can have these ducted modes in the magnetosphere, and if you're sending up a signal below FOF2, probably up to about 5 megahertz, you can get a reflection off the ionosphere in the opposite hemisphere in the conjugate magnetic point. And in this case here, these are observations from Hobart. About 270 milliseconds later, get an echo that will tell you something about the conditions along that long path. It can tell you something about the electron density or the turbulence, but it's a very lossy mode. And in this case, they were transmitting effectively with 17 kilowatt peak power and had a fairly large antenna. But look, with modern signal processing, maybe you can retrieve a little bit of that, but I think it's a bit of a stretch, but we'll see what, just keep that in the back of your mind. Look up long delayed echoes, and there are some folks that have been using these to study the magnetosphere. And then the final thing I just wanted to mention was kind of another aspect of ionospheric sounding, actually using lightning as an ionospheric sounder, and some spectra from my place showing this is as sunrise approaches. Often you'll see these interesting limits to the spheric frequency, and this is a lightning storm off the east coast. As the sun rises, the FOF2 is changing, So you can sort of use the lightning as a poor man's Ionosonde. But the other thing I've been looking at is with my SDR, I can get down to sort of millisecond time resolution on some of these spectra. And here's an example where you start to look at some interesting effects of the ionosphere on the lightning itself. And this envelope here, as the frequency changes, there's a delay because you're getting longer path lengths at the higher frequency. So you can start to make some interesting measurements using lightning as a poor man's Ionosonde, essentially. So that's it for me.
Fantastic. Thank you, Andrew. Any questions for Andrew?
Jackson Pollock.
Yes. Yeah, they're blue poles. They certainly are. Yes. Yes.
Is there any indication of TEP, trans-equatorial propagation, in the data that space weather produces?
Yeah, that's there is a TEP. They give you a little bit of a primer on TEP, but they don't really have any products that talk to that. Yeah, that's right. I think you might be able to derive some indication from maybe the FOF2 maps potentially, but you kind of need to know what the ionisations do. You need to know where the maxima that are running around the equator, and that's to do with the plasma flow in the equatorial region where you're getting convergence of plasma. And that varies in latitude during the day. But I don't think there really is. The best way, I think, you can see that, of course, is by looking at the maps of the propagation, so the FT8, distance of the FT8 propagation. That would be my quick thought on that. But yeah, maybe there's an opportunity there for amateurs to have a think about that.
A comment for Stephen is one of our amateurs, Andrew Martin, produced a chirp sounder on 6 meters, and he was able to see ground reflections right round the world.
Wow. Yeah, well, I guess that's the thing. You know, Stephen's got a range of 1,000 kilometres on his system, and the Bureau ones really, they're interested in vertical sounding, but it's interesting to be recording, you know, for much longer times. And of course, this is how these ducted measurements are operating. You know, you're listening for, let's think, it's 150 meters per microsecond, and you're 270 milliseconds later there. So you're thousands of kilometers. You know, you've kind of got a window. So it would be interesting to see what happens.
Those of us who have spent a lot of time on HF are aware of a lot of anomalous propagation that is not explained by any of this.
Yes.
I mean, long path is the obvious one, whereby, say, we can work from here to Europe.
Yep.
And on that path, which is a longer path, we will have signals that are 20, 30 dB stronger than you ever get on the short path.
Yeah.
And it's because you're doing some kind of caudal or whatever.
These ducted. Yeah.
Nobody's bothered to study it.
Bouncing between.
The other anomaly, you're talking about long delayed echoes. I've experienced long delayed echoes. Heard my own voice coming back to me, and that was on 14 megs.
Wow. That's fascinating.
So not a lot of my own voice, but just a bit of it.
Right.
Very eerie. It's scary. But I'm pretty sure nobody was playing tricks on me or anything stupid.
Yeah.
What was the delay?
Naturally.
What was the delay? I'm guessing
Just about long enough for me to hear
it'd be kind
half
of
a minute of my own voice.
right.
Yes.
But
Half a minute delay or an echo.
Half a second.
echo.
No, an echo.
Yeah, the
It
echo
was-
was probably 0.1 of a second.
Yeah, something like that.
Yeah. Well, if it was
Still, that's pretty impressive.
something like quarter of a second, it'd be from the other hemisphere. And the theory kind of says, less than 5 megahertz, but that's based on actually this paper here, which kind of back in this is 87.
Quarter of a second's 36,000 kilometres and back, geostationary.
The thing with operating as we do as radiometers is that we're there at very strange times.
That's right.
And somebody is at the other end at
Yes.
very strange times.
Yes.
So, and you'll get another anomalous one that has always got me is that in the middle of one of our radio contests, you'll have a dead band, absolutely nobody on it. You know that there are hundreds of people all over the world operating,
Yes.
but you can't hear anybody.
Yes.
You make a call on that dead band, as I've done in the past, and say I get a whole stack of calls from W9 in the Chicago area.
Right.
Only that one
Only
area?
that area.
I've had a similar experience of Spain.
Right.
Call, and I get half a dozen signals in Spain. And when I checked where they all were, they were all within 10 kilometres of Barcelona.
Right.
So it's like a searchlight.
Yeah, okay. Right. Very narrow.
And, these things, you can work it all out and say it's this and it's that, but we really don't know.
That's right. That's where, maybe some of these exotic modes could come in. You get these field aligned features. Well, I'm just waving my hands here, but yes, making a log of these is pretty important. So I encourage, and you've probably got logs of these things, so we just need somebody to have a look at it and interpret.
I mean,
these
it
things.
sounds like sporadic E could be involved.
Could be.
It probably is
Yeah.
for that. That was my theory on it. But there's lots and lots of these. The other one with these radio contests that we do, where thousands of people are on all the time for 48 hours, is that the predictions are way off.
Yes.
So they'll say the MUF is, say, 15 megs or something, and we're all chatting away on 28 megs.
Yes, no worries.
All over the world.
Yes, that's right. Yes.
So there's, and in fact, if somebody really wanted to study HF propagation, if they could get hold of the data from the contested adjudicators, which would tell you who spoke to who at what time, and had the patience to develop a massive computer system to analyse it.
That's where you can.
Do you give proper reports, or is it always 5-9?
Doesn't matter.
Craig!
Doesn't matter.
Someone had to go there.
It's whether they contact each other,
Yeah, that's right.
where the propagation is going on.
Well, so I guess my comment there is that's a great thing to study. And when I was at the conference last year, I heard that there's quite a lot of interest now in sort of amateur ham collaborations, and there are some very active people. South Australians look like they're pretty active. It'd be great to get together and start up something a little bit akin to the US HamSci network and do something along those lines. But that's valuable information, which should be used in some way. One question I have too is, like I see these plots, and you know that people are transmitting and receiving, but is there a way of knowing when people are transmitting and not being received? Like, if you had a log also of if your system is transmitting,
when they transmit, but then there's nothing.
there's nothing coming back, which would kind of help in your situation, these dead bands.
There is a system which we've currently got where if I call on CW, because the machine can read CW, and I can look on the computer and it will tell me where I'm being heard.
Yes, okay, yeah.
So
yes,
I don't
right.
actually have to work talk to anybody,
Right.
but there are monitoring stations all around the world.
Yeah, that's
so
right. Yeah,
I can
yeah.
see where the propagation is going.
Yes, that's right. I mean, it's sort of akin to these PSK
Andrew,
reporters.
see, there's the Whisper network as well.
Yeah, the Whisper. Yeah, I kind of look in the Whisper, and this is I was looking this afternoon at the PSK reporter to look at the.
Taking up your point around, is there a record of when you transmit but you're not being received? That would be a very simple change to the Whisper record.
Yeah.
Because you only ever upload received signals.
That's right. Yes, that's right. Yeah.
But you could also be uploading transmitted signals as well, so you could do that correlation.
Yeah, I guess there might be equipment problems too. You might not have your antenna plugged in or something like that.
There might be 100 reasons
That's
why
right.
it
Yeah,
doesn't go through.
That's right.
But everything has to be right for it to go
Correct.
through.
Yes,
The
that's
more
right.
records, the lower that error rate becomes.
Yeah,
So
that's right.
it's-
And then you could correlate it with this basically.
Yeah.
And that's where it gets interesting.
Yeah, that's right.
That's
Yeah.
where and FT8's a very
See
good
the
tool for
maiden
that
head
because
numbers.
you only have to transmit a
Yeah,
couple of
yeah.
cycles,
Sure,
go to
sure,
PSK
yeah.
reporter, and it'll just draw the map of everyone that's hearing you.
Yeah. Yeah, exactly right. Yeah. So look, I think there's some really interesting things, whether it be using ionosondes, but even just to you transmit receive information to understand a bit more about how the ionosphere works, and these strange modes. So there's lots to do still. That's good. It's not solved.
It's boring if it's solved.
Yeah, that's
I know,
right.
correct. We're all about novel communication.
Yeah.
It's exactly what Martin's talking about.
Yeah, that's right. Yeah, it's good.
That's enough
So-
meteors.
Yeah. So actually, I listened to VK7RST and I'm going to test all the meteors, 30 or 40 per hour. But I see on that very short path, which is just to Devonport. It's only 200 kilometres, 230 kilometres. Yeah,
6 metres.
at 6 metres.
Okay.
Great.
Fantastic. Can we show our appreciation of Andrew? Thank you very much.
Thanks very much for the PC solution.
Thank you, Barry.
Good, yeah, like this.